All right. Well, thank you all for coming. We have 3 of the course participants here. Robert, right? And you're joining us. You're right here in Austin.
I am.
All right. And what do you do?
Software development.
Software development. Welcome.
Thank you.
And then we have John, who is also from Austin.
Yes, I am.
And you do?
Software development.
What else?
3M.
3M, I see. Okay. And can you repeat your name again? My hearing is not. Yes, you please.
Dacio. Dacio.
Dacio?
You got it right? Yeah.
D-A.
CIO.
I'll write it down. I'm very bad with names. I apologize. And he drove in all the way from Dallas for the occasion. So
Made it just in time.
we applaud you for fighting traffic and having this level of dedication. Were you slicing and dicing through traffic to get here? Very good. And then we have another special guest, Aaron from MathWorks. You want to come get on camera for a second so people know what you look like? They've corresponded with you. So Aaron flew in from Boston for the occasion. This is actually the first time we've met Aaron today, so welcome. And Aaron brought us 2 presents. Maggie and I each got a T-shirt. And those of you who have worked with MATLAB know what that means. Essentially, if you know that, you don't have to take our course. Because, right? And that's the back side. And the idea was for me to spill coffee on me so I could wear it, right?
We didn't really get around to that.
We didn't get around to it. And then also a laser pointer, so... Okay, now why isn't it working?
Oh, there
There it is. So I'll play with my dog with that one. Thank you, Aaron, and welcome.
Thank you.
So, let's see. There are other people worth mentioning. First of all, Maggie, who is way too camera shy to come up here. Right? Come on, a glimpse. Come on.
But you
Come
can,
on.
you can hear my voice.
Okay.
My voice.
Well, at least come and show your fingers. That's what people know you for. That way they know you're actually here. And then, well, yeah, I was going to go around that way. We have Josh, who did our Monday morning laughs and other. Come over here. Josh is not shy. Might I add, Josh is looking for a job, so just a small advertisement to the world. I think you want to come this way. Okay, so that's Josh, and Josh provided enough humor to keep us going, and was our media guy, and then also kind of made sure that everything was in place before we went live. So thank you, Josh. And
anytime, you know that.
Fantastic career.
Thank you.
We also have Piers, our second oldest son out of 3. Are you going to come up here?
No.
No? We have a very camera shy family here. So Piers last year spent a lot of time putting materials on the platform, and this year only fortunately had to do a little bit of maintenance because most things were actually in place. We have Sejal. Sejal, you want to come up here? Or? Very good. See, Meg, once you don't want to come up here, that's it. So Sejal is with the Center for Teaching and Learning here at UT Austin, and she's provided a lot of support and interaction with edX as well. And we have one student who was brave enough to come from my class, who therefore also went through the course, but also got to suffer through my lectures. And we have many people who helped out last year. We have Sen Yu, we have Chen Han, we have, let's see, I think that's it, huh? Am I missing somebody? Anyway.
For the other MOOC.
For the other MOOC, what? Andreas?
Andreas?
Okay, so at the end of last year's course, we did a presentation called Last Laugh, and that time I actually talked about how slicing and dicing helps with mapping linear algebra onto massively parallel computers. And if people want to see that presentation, it's probably somewhere. So maybe I can post that. Well, I think it's somewhere. I'll find it. It's on YouTube. This year, I decided that we were going to talk about reflections, and I meant that in two different ways. We're going to reflect upon this course, and then also, as part of the course, we often ran into a linear transformation that was a reflection or a mirroring. And therefore, I'm going to revisit that topic at a little bit more advanced level, since we have, a little bit more linear algebra under our belt, and therefore we can do that now. So let's first look a little bit at this course. So we offer the course on edX. And edX is a non-profit that was started by Harvard and MIT, and then eventually the University of Texas became a charter member, at which point there was a call for proposals to put some MOOCs together for the University of Texas, to which we responded. And then originally there were 9 proposals selected, and then 8 of those actually were offered in 2013, 2014, and I think the 9th one in fall is going to start this fall. So they delayed it. So we proposed a course that eventually became Linear Algebra Foundations to Frontiers, where obviously Maggie came up with a good acronym, and then we fit the name to it. It worked out okay. And it was selected to launch in spring 2014, and Maggie and I are the instructors. And there was an entire team behind that to actually develop the course. We'll get into that in a second. And then we decided to offer it again this spring, and we just decided to offer it again this summer. So, we actually thought if we just get enough sponsors together, surely people will pay attention to us. So we kind of went and collected sponsors. The important part is that the University of Texas system invested quite heavily in these MOOCs, made a considerable investment. And then other funding primarily came from the National Science Foundation. We actually have a very large research grant to revamp the linear algebra software stack. And quite a bit of that we try to actually work into the MOOC so that people get that glimpse of the frontier. These days, we're kind of self-funded. Seems like money has run out, or I'm not sure. I guess we work for food is what we do. And it's actually based on a course that I teach here on campus, and we have one student from that course here. So at least 1 out of the 80 students likely enough to come for food, right? So what we do in that particular course is we use the materials that were developed for the MOOC as the resource, like a book, and then sometimes a lecture in class, sometimes we do other activities. And our third son wants our attention, and he's just going to have to wait. Maybe I'll just turn this off. Here. He's been texting me, Maggie. I think he needs your advice on cooking. There we go. I can edit that out.
Right.
I think you better take that outside, though, Meg. All right, so I'm back. Now, last year something very interesting happened when we finished. There was a gentleman who had taken the course, who had been extremely active on the course. Essentially, we would put out a week, and he immediately would send us a bug report of everything that needed to be fixed. And we'd then go and fix it, and then the next week he'd have another bug report. And his online name was Richard of Dale. And Richard of Dale was a participant in spring 2014. And when it was all over, he thought we needed coffee. So he actually sent us a check to buy coffee with. The problem is that Maggie and I only drink decaffeinated coffee, so we haven't spent that 300. So we decided to spend it on today. So today is brought to you by Richard Dale, our good friend who helped us out so much last year. We have not met Richard, but I've corresponded quite a bit with him. And so we have decided to invest it in this last laugh. So the last laugh is on Richard. Okay. There are many contributors. We actually went through most of this. So everything in black were actually people who at one point in time helped out. The ones in red are the ones who were left for this last spring's offering. And we got it down to, I think, where we can now handle it with a much smaller team. And it actually was quite manageable. So what's the philosophy behind the course? The idea is that instead of sort of teaching programming in isolation or teaching mathematics in isolation, the idea is to show that if you create the right abstractions in mathematics, then the abstractions in the programming come hand in hand with that, and all of a sudden the programming helps explain the mathematics and vice versa. So that was always what we intended to do. When you create this kind of course, who actually shows up? Now this is a very busy slide. So these are from the course analytics on edX from spring 2014 and 2015. And what do we have here? This is actually enrollment as a function of time. Now, this is actually where the course stopped. So this is really where you should cut it off and then compare it to the one on the right. But what you notice is that there was a very similar ramping up of the participants, except that we hit about 30,000 or 28,000 or so the first time we offered it, and the second time we hit about 16,000 or so. This is the age distribution. So this is 18 right here, 37, I don't know why 37, 56. And you notice that it's a relatively mature crowd. I believe that about maybe 35% or so is less than 25, which looking at this doesn't make sense, does it? Maybe, if you go right here. So, but again, there's not much change from last year to this year. And then this tells you what the background, educational backgrounds of the different people are. And this is, of course, impossible for you to read, but these people have only a primary education, middle school, finished with high school, finished with middle school, finished with high school, associate degree, bachelor's degree, etc. And what you notice is that actually quite a few people who took the course already had a doctorate. So a lot of those people actually had doctorates in, say, science-related subjects and just felt like they needed a little more. On the other hand, quite a few just had a high school education, so one would assume that these might be currently in college, perhaps, or preparing to go to college. Here's the one that we've tried to fix real hard and clearly not really managed. Male participants versus female participants. This is about 15%. And then we tried really hard to increase that for this spring, which is why we ended up with about 15%. Okay, so we had no impact on that whatsoever, and it seems like MOOCs in general don't attract female participants as well as they do male participants. You know, it's worse for technology-related subjects, but it's actually across the board. So even the course in jazz appreciation, I believe, has a problem with attracting enough. Right, Sejal?
Embedded systems also.
Yeah, embedded systems is also about 15 to 20%, right?
Yeah.
So it's.
The real version is not that.
What is it in the real version? On campus?
0? I don't know.
0?
No, it's not true. Because
Okay.
PME students are required to take.
So now you're starting to realize you should have sat a little bit closer, right? This actually is a little easier to read. So what do we have here? We have two important curves here. First of all, along the x-axis we have time. So this is January 2014 when we started the first offering of the course. This here is January 15th when we started the second offering of the course. And this is where we are right now. Now, these are statistics from YouTube on who is watching the videos. Not everybody watches the videos on YouTube, so this is not, you know, a complete picture. The blue line tells you how many minutes are being watched on the given day. Okay, so this is on the granularity of a day. And what you notice is that the course opens, everybody has a look, everybody goes running. This pulse here is actually because we had weekly assignments due. So that created kind of a pulse. And of course we also released new material. And then eventually we got rid of all of the deadlines. And the pulse went away and it kind of became smoother. And then everybody heard that we were about to close the course, and then the course closed. But we actually left the materials open all summer. So there was sort of a sprinkling of people still watching through the summer. But clearly, you know, so everybody, these people had access to all of the materials. But what you kind of notice from this is that people do seem to need to have an actual course going in order to stick with it. At least that's one possible way of interpreting this. And then finally here we closed the course altogether, and there was still a sprinkling of people watching. And then we reopened, and the pulse was back for a little while because we had deadlines, and then the deadlines went away after the first exam. And now things are starting to ramp up again because people realize they have to get things done.
What is the significance of you closing the course in the late summer, early fall last year?
Right here?
Right. What is?
So when we opened registration for this spring, we decided that it was time to close registration for the previous course so that people would instead go to the new course that was going to be offered. Okay? So that's why we made that decision. And how we're going to do that now that we're going to offer the course again in a few weeks, I don't know. This is the interesting one. Well, this one is also interesting. So here we have average percentage of video watched. Okay, so a given video someone watches, what do people do? They watch 15 seconds of it, they say that's enough for me, they move on to the next video. We actually hit somewhere between 70 and 80%. So on a typical video of ours, 70 to 80% of it is actually watched by an individual when they started, which is pretty good. I have some lectures that are full lectures that I have up for my graduate course, and I think, you know, that number is more like 10%. Okay? So the thing to take away from this is that it does seem like if you cut everything up into very short videos, people are much more likely to stick with it. And that's something that actually, even over the summer, well, you notice that up to here people kind of stuck with it, and then these were probably people who were just sort of randomly stumbling upon the material serving YouTube, and those people would have a look and walk away from it. So it was a little lower. But still, we're quite pleased with those statistics. You know, nothing to sneeze at, you know. 1.7 million minutes wasted. People watching our videos. Right? That's like 3.5 years. All right? Now you can say, well, there's a lot of people out there, but still, it's nothing to sneeze at. What kind of reviews does the class get? I'm not sure if I want to show this because a new one just came in. Let's see. Why isn't this not popping up? Here we go. So this is the latest one that just came in. And that's a little disappointing. We only got a 4 out of 5. But actually, pretty consistently, we've been getting 5 out of 5. So This person wanted to know about determinants, which is just a topic that should not be taught. Well, I mean, you need to have a notion of what a determinant is, but a determinant in by itself actually has very little use beyond 3 dimensions, so we don't teach it. And then SVD is really, we consider, a more advanced topic that one should go and see in a more advanced course. So, well, it's okay. I mean, I still think that those are positive comments, because comments to help us improve the course are always welcome. Here's someone who really thinks it's a little too long, and it is. We give a full college course as a MOOC. Most people do it as 6 to 8 week courses that are part of the course. We chose not to, and yes, it's a marathon. And then some people found it very useful, and some people just really decided to pour their hearts out. And we thank them for that, because sometimes we need them. Anyway, people can go and read those themselves. Last year, hang on. Okay. Last year, I showed the funniest post of what was posted. This year, we didn't really get any funny posts. There was one post that I could have put up where somebody said, Robert Elbert, Van de Geyn, Einstein, coincidence. And anyway.
You should show the Facebook post.
Huh?
You should show that.
Oh, the Facebook post. Some of the Facebook post. Was that on Facebook?
So, I printed it out and put it on my office.
Okay. Well, people can go look at our Facebook presence. Actually, thanks to Josh, we have quite a tremendous Facebook presence. We have, I think, 1,250 followers or something.
Yeah, that's many likes.
So likes or whatever it's called on Facebook. Now, notice how much we needed Josh. I don't even know the language. But this one was very funny. Hopefully you had a chance to read it. Anyway, so let's move on to the other part, which is a little bit more of a technical talk, as opposed to reflection on the course. So let's revisit reflections. And we saw reflections at a number of different points in the course. The first one came in a homework in the second week, where we introduced the notion of a linear transformation. And a linear transformation, you can either stretch a vector first and then transform, or transform first and then stretch. Or you can add first and then transform, or transform first and then add. And one example that you can reason through is a linear transformation is when you mirror with respect to some line. So that was a little exercise in the second week. We also had an exercise called Timmy, which helped people visualize what a linear transformation, or how to translate a linear transformation into a matrix. And in the process, we can see what the course sort of looks like. So when you enter the course, you see some information, and then you can go to courseware, and you can go to a week, and then we started always with opening remarks. And we had an exercise called Timmy 2-space, which was a little stick figure. This was an exercise suggested to us by our colleague Ellen Klein. And the idea was, if you think of this stick figure as being consisting of many vectors pointing to different points, then what matrix will transform those vectors into the target? And some of these were reflections. For example, this right here is clearly a reflection with respect to the y-axis. And the way to determine the matrix, which you have to enter up here in the top left corner, oops, I have this in this top left corner, is to look at how the the first unit basis vector transforms. So the vector 1, 0 becomes minus 1, 0. And we learned that that's the first column of the matrix. And then we have the vector 0, 0, 1, which actually becomes the vector 0, 1. And that then becomes the second column of the matrix. So that this is the matrix that you then conclude does the mirroring. And then if you say Timmy, you get to see whether Timmy indeed is transformed to the target. And that teaches people about the fact that a matrix represents a linear transformation, and how to determine what entries go into the matrix comes from looking at how the unit basis vectors are transformed. Now this time we had a participant who I think is a software engineer at Yahoo. I should have looked that up because I would hate to get that wrong. Let's see here. Who put a variation on this together where you can enter the matrix right here, or you can enter a preset matrix. So if you want the matrix that does a mirroring on the x-axis, notice that it fills in the matrix right there. You can then optionally show Timmy again, and then you can point at the different points on Timmy and see where those points are reflected to. So these were some activities that centered on mirroring, where they were always in the 2D plane, because at that point we were still trying to get our bearing as to what linear transformations and matrices are. So, moving right along. Why does this keep doing that? Let's review some other things that we learned in our class. Okay, we learned about projection. So if we have a vector here, we can look at the vector, and we can look at the subspace of all vectors that are orthogonal to that vector. Okay, so just to sort of illustrate that, does someone have a pen handy, or a pencil, or something? Oh, here we have it. Here's our vector. So, notice that if you have a vector, then that vector, you can ask the question, what vectors are all orthogonal to that vector? And notice that as you move that vector along, you move that space, subspace around. And therefore that vector really also defines the subspace of all vectors orthogonal to it. Okay. So, and then if you look at it at just the right angle, can I do this? You look at it, no, there we go. If you look at it at just the right angle, then you get that blue line as representing an entire subspace. All right? I don't think this prop is working so well. No. Okay, so keep that in mind. Now, what we learned was that if you have another vector, you can ask the question of what is the component of that vector. Okay, this didn't turn out. There's actually a very faint gray box here if you look very carefully. But anyway, so imagine a rectangle there. Notice that vector x you can think of as having a component in the direction of v and having a component in the direction orthogonal to v. And if you do this plus that, then you get that. That's what you learned in week 1. Okay? So, the other thing you learned was that to find out what that vector is that is the component in the direction of the vector v, you take the inner product of v, you divide by the square of the length of v. That is how much you need to go in the direction of v. In other words, that's by how much you need to multiply v to get from here to there. Okay? And then you can rearrange that, and you can actually put x at the end, and that then gives you a matrix that projects x onto the direction of v. All right? Now, similarly, you can then say, well, what is the component orthogonal to this? Well, the component orthogonal to this is just the vector x minus this vector that's the component in the direction of v, so that's x minus that, which you can actually rearrange as follows, and that we all learned in week 11. And this then is the matrix that projects onto the direction of v, and this is the matrix that gives you the projection onto the space orthogonal to v. All right? So that's projection, and that was part of the class. Now, let's look what we can do with that. Well, first of all, things get a lot simpler if we make our vector of length 1. Okay, so you take your vector v, you divide it by the length of v, you know that u then has length 1, so you take your vector here, and actually u is meant to be, I don't know why there's two vectors, oh wait, this was v, now we're creating u, and if you do that, then looking at what this vector is in terms of u becomes a little simpler because the v, if we go back here, while here we have to divide by the square of the length of v, now that becomes 1 and goes away, and the matrix that projects in the direction of u becomes a simpler formulation of u transpose. And similarly, if you look at the matrix that projects onto the space orthogonal, you get a simpler expression as well. So things get simpler. Vectors of length 1 are good, and we've seen that many times in the course as well. Okay. If she wants Legos, it's right over here, Xianyi. You can play with Legos over here. All right, we have a very young participant, the ripe old age of 2, I think. Right? Okay, so now we have reminded ourselves of how projection works. And what can we do with that? Well, notice if you go and compute the component of x in the direction of u, and you subtract that off of x, then you get your projection onto the subspace orthogonal to u. Okay, that's because we saw that this plus that was x, and therefore this minus that must be this vector right here. And notice that this here is orthogonal, so we know that these meet at a right angle. What we can then do is say, what if we go the same distance further in the same direction? Right? So you subtract off u transpose x once again. And what you notice is that you get a vector on the other side that is mirrored with respect to this subspace right here, which was defined by the vector u, which was orthogonal to it. Okay, so how does that work? Okay, you probably took a course in physics where if you had some kind of thing sticking out of a mirror and you asked the question, well, how does that really look on the other side? Then it really sticks out on the other side. And what we're doing is we're looking at the mirror from the edge. All right, you got the point? I don't think the mirror itself is working so well here as a prop. Okay, so our blue line, which really represents the whole subspace, now becomes a mirror through which x is reflected into this new vector. And if you compute what that vector, that green vector must be, notice that it's x minus this vector, or actually x plus this vector, plus this vector, which you see right here. And if you manipulate that a little bit, you get this. And if you manipulate that a little bit, you get this right here. Okay? So this then is the matrix that performs the reflection, that performs the mirroring. Okay? And notice that it's just defined by the vector u of length 1. And other than that, it's a matter of just applying that matrix to a vector to reflect it with respect to this blue line. You got it? Now that particular matrix has a special name, and it's known as a Householder reflector. And if you take a graduate course on numerical linear algebra, you find out that everything is about Householder transformations. Okay? They're just everywhere. You want to come up with a practical algorithm for computing linear least squares, solution, you use Householder reflectors. If you want to compute the eigenvalues of a matrix, you first do a transformation of the matrix, which depends on Householder transformations, or Householder reflectors. So who was Householder? Mathematicians are people who like to look, well, so there's this project that traces the genealogy of mathematicians. So you can go, if you're a mathematician, have you done it yet? Yes?
Yep.
Who's your ancestor way, way back?
Oh my gosh.
How far back does it go?
I don't know if I actually looked all the way back at the source, the root. We could look it up.
The last time I looked, I went back to Bernoulli.
Oh, which one?
Well, the son was the PhD student of this father, so both. But anyway, why isn't this working? Oh, here we are. So if you go to the mathematics genealogy project, you find that Householder got his PhD at the University of Chicago, and there are only 5 people who graduated under him listed, although this is often incomplete, so one shouldn't take that too seriously. Although I believe Householder actually graduated very, very few people. If you click on probably his most, well, undoubtedly his most successful student, Pete Stewart we know him as, you find that he graduated only a few students as well. And this is actually accurate. He only graduated 6 of us. And you notice that I'm actually there. All right? So Householder was my academic grandfather. That's how it works. And somehow that means that I must be important, right? But it certainly means that I have a certain feeling about Householder reflections, right? I think I actually have more than 7 descendants, but I always lose track. So I think this claims that I've only graduated 4 people, and I know that I graduated 4 people in the last 2 years. So I think I graduated, and none of these were them, so I must have more than 4. All right, so little side tour there. And so let's get back to reflecting. So we have our vector x, we have our u that defines our mirror, and if you apply the Householder transform, or the Householder reflector to it, you get the vector y that is its mirror image. What do you suppose you get if you apply the same Householder reflector to this vector y? Don't be shy. X. Pierce got it. Okay, no, it's a mirror. You mirror from x to y. You mirror again, you better get x back, right? So, that's actually kind of interesting. So let's see. What happens if you take x, you apply the Householder reflector to it, and you apply the Householder reflector to that? What do you get?
The initial vector.
The initial vector x. Very good. What does that mean about the product of these 2 matrices? In other words, the Householder reflector with itself.
Identity.
It's the identity, right? Because this matrix undoes that matrix, and they're square matrices. Okay, so we get the identity. So you can reason through the fact that this must be the identity, or you can do the math. You can take this, you can multiply it out, you can recognize that this and that simply offsets each other, and you get the identity. So indeed, it is its own inverse. That's what you would expect from a mirror. Okay. Obviously, we should have taken a different... okay, that's kind of corny. Never mind. All right. So, we've now figured out where, if you know what the mirror is, how do you compute the matrix that does the mirroring? And what we're going to do next is we're going to turn things around a little bit. And we're going to say, what if we have a vector x, and we have a vector y, and we would like to know what this mirror is that will take x into y? In other words, Now notice that the mirror itself is defined by u. So the question becomes, how do you compute u from x and y? Now there's some simple observations here. Let's have a look at this vector. Okay. That vector is easy to compute. In week 1, you learned actually that that vector is just the vector x minus the vector y. Okay? Now what's curious about that vector and that vector?
Parallel?
They're parallel, okay? So notice that inherently if this is reflecting with respect to this mirror, then this vector must cross the mirror at a right angle, and therefore it must point in the same direction as this vector u. So it is easy to compute a vector in the correct direction. Okay? So then how do we get from this vector that points in the right direction to the vector u?
Normalize.
Normalize it to 1, right? So all we do is we compute v, which is easy, and then we compute its length, and we divide by its length, and we now have the u that defines our mirror. All right? Now, this turns out, now that, by the way, I guess coming up with a vector of length 1, we saw several moments in the course. I don't know, when was the first time we saw length? That was week 1. And the first time we took a vector and made it of length 1 was probably in week 11, when it became kind of important. And we were starting to compute orthogonal bases. But we probably saw it a couple other times. So it turns out that the case of a householder transformation, a householder reflector, that is most important is the case where you're given a vector x, okay, here are its components, and you want to reflect it into a vector that has zeros below it. Okay. Now, there's a couple of things to observe. Mirroring preserves the length of the vector. Okay? So, we know that if this vector has these components and is called x, then the vector in the direction of the first unit basis vector has to have its first component be either the length of x or the negative of the length of x. Or Field, who left, likes to go and look at the complex plane, and then it gets nasty, so let's be happy that he left. All right? So, the question is, how do we compute the mirror for this, the householder reflector? Well, we just apply what we just learned. We compute this vector right here, which notice you just take this vector, you compute its length, and you subtract that off of the first element of it. And bingo, you've got the right direction. And then all you do is you normalize it to have length 1. And bingo, you have your householder reflector that takes your vector x and makes it point in the direction of the unit basis vector. And this defines the mirror. You got that? Now, where have we previously seen a case of a matrix that takes a vector and makes it into a vector where all but the first element are equal to 0? Okay.
Reduce row?
LU factorization, reduction to echelon form, etc. Very good. And that was, the first time we saw that was week 6. Okay. So notice that if you take this householder reflector now and you multiply it times this vector, you get the vector that has zeros below the first element. Okay? So what can we do with this? Well, before we go on, let's observe a couple more things. Notice that this matrix is inherently square and symmetric. Right? Take the transpose of it, you get the same matrix back. That's something we learned in week, symmetry was week 3, right? What do we know? We already saw that if you take the matrix and multiply it times itself, you get the identity back. Right? So it is its own inverse. which is because you take a mirror, you do it again, you get the vector back. Okay, now it's symmetric. So what happens if you take the matrix, you transpose it, and you multiply it times the Householder reflector? Well, it's a symmetric matrix, so you get that back. And we just saw that it is its own inverse, and therefore you get the identity back. Now, let's call this matrix Q, and let's therefore call this Q transpose. Square matrices. What do we know about Q transpose times Q equal to the identity? We know that it must have mutually orthonormal columns. Okay, that's something that we observed, that we talked about before we got into Gramschmidt orthogonalization in week 11. You with me? Okay, what does this buy us? Well, it gives us an interesting algorithm. What is it that we like to do with matrices to make them simpler so we can compute solutions with them? I mean, if we wanted to solve with this matrix, that's nasty, right? No. A triangular matrix is so much nicer, right? So with LU factorization, what did we do? We used Gauss transforms that we applied to the matrix in an effort to make it upper triangular. And then everything became beautiful, right? Now notice that you can look at this matrix, you can slice and dice it, expose the first column. You can then focus on the first column, and from that first column, compute a Householder reflector that has the property, so let's just isolate that first column, that has the property that it zeroes out the elements below it. Okay? What you learned in week 3 is that a matrix times a matrix is the same as the matrix times the first column, the matrix times the second column, the matrix times the third column, etc. So what you notice is that this first column now gets zeros below, and the rest of these entries are still X, but they really meant to be updated to something new. Okay? So that's sort of kind of like applying a Gauss transform, except that we're using a Householder reflector, sometimes called a Householder transform, instead. Then you can move on, and you can look at this right here. Compute a Householder transform from it to introduce zeros here. If you put a 1 and zeros here, then when you multiply this all out, it leaves this row alone, it leaves these zeros alone, and it introduces these zeros right here. Okay, so again, we're using a Householder reflector now to make progress. And if you do that again, you can introduce a final zero. You end up with an upper triangular matrix. Upper triangular matrices are wonderful. All right? But things get better. Let's go back to the original matrix. What we did was we applied a Householder reflector to it in an effort to make these into zeros. Right? Let's call that matrix H0, H for Householder. Fair enough? You can then, so then we just have H there. Then you can apply another Householder transform to introduce these zeros, and another Householder transform to introduce that zero. Okay, so now we have the product of a bunch of Householder transforms. Now the cute thing is that if you multiply all of these Householder transforms together, remember that they had orthonormal columns. When you multiply them all together, you get yet another matrix that has orthonormal columns. Okay. So let's call it actually Q transpose here. What does that mean? It means we have a matrix A to which we applied a matrix with orthonormal columns, that is a square matrix, to make it into an upper triangular matrix. Okay. We have this, we have this. You can then multiply both sides by Q. But remember that Q transpose Q was the identity, and because it's a square matrix, that means that Q times Q transpose is also the identity, because Q transpose is the inverse of Q. Right? And what you get is A equals Q times R, where Q has mutually orthonormal columns, and R is upper triangular. Right? That's known as the QR factorization. Where have we seen that before? Right? Well, in week 11, we had an algorithm called Gramschmidt orthogonalization, which we showed was equivalent to computing the QR factorization of a matrix A. Right? So, we also saw, if you did the enrichment in week 11, that for some matrices, if you applied Gram-Schmidt, round-off error could cause all kinds of trouble, and you would end up with columns in Q that in theory should be mutually orthonormal, that in practice weren't orthonormal at all. And that was all due to round-off error because we were doing this on a computer. So it turns out that the reason why what's called householder QR factorization is so important is that it is an alternative algorithm that has very nice numerical properties where even if a little bit of error comes up and you start with that same nasty matrix that we started with before, you can actually compute a matrix Q that has mutually orthonormal columns, essentially to machine precision. And that's something that you guys learned all in numerical linear algebra in graduate school, right? So that's one of the main topics in the first couple of weeks of such a course. And it turns out to be just an incredibly important tool. I mean, what, half the class was on, in one form or another, focused on householder transforms. Let's see. I mean, it starts with linear least, well, QR factorization or orthogonalization, linear least squares. Then you move on to eventually showing that it's important for computing eigenvalues and for the singular value decomposition, right? And that's pretty much the whole course. Very important topic. Too advanced for our undergraduate course, but a great place to start the graduate course. So, the question is, do you want to laugh some more, right? And there's a couple of opportunities. We have this webpage set up where one can get the notes for this class, but also notes for the graduate class that I teach, in which the householder transform reigns supreme. And those notes are called Linear Algebra Foundations to Frontiers, Notes on Numerical Linear Algebra. And frankly, if you really put some effort into this undergraduate course that we just completed, I believe you're ready to go on to these notes. Now, of course, just working with notes may not be the way you learn, so you may want to wait for the MOOC on this, which is probably not going to happen, so you may have to wait a long time. But at least you could sit around hoping that there would be this fantastic MOOC all about the household.
We can take that class here?
Transfer. Huh? You can take that. So I take turns teaching that class, and I will be teaching it next spring. So I'll teach it next spring. Hopefully I'll do a better job of taping the lectures that time. That might help people. This fall, a colleague of mine, George Piros, will be teaching it instead.
The graduate class?
The graduate class, yeah.
Oh.
So, as we always end our emails, laugh long and prosper. And I'll take questions now.